Hello, everyone. In this talk, we are going to be talking about how Galileo and Johnson Labs work together on helping our users adapt their own LLMs and NLP models towards their own specific data with real high quality insights from the models and data quality insights to quickly iterate over your models faster. This talk will be presented by Franz on the Galileo team, Christian on the John Snow Labs team, and myself, Yash. I'm one of the co-founders here at Galileo, and we're super excited to dive right into presenting and showing you guys some of the some of the awesome insights that come out of Galileo once you pair it up with Johnson Labs. Amazing. I'll hand it off to Franz to dive right into an amazing demo, and we'll pick up the rest of the talk after we see the demo in action.
Hello, today I will give a short demo of how to use John Snow Labs with data quality from Galileo. First, we choose a model by checking out the model hub from John Snow Labs. There's a couple of oncology models. Once we found a model, we can create a Google Colab and install our dependencies. You install data quality with pip install data quality, and then you initialize Spark and you load your pipeline. Once the pipeline is loaded, you can load your data set, and then it's time to create a Galileo project. For that, you import JSL project and you pass in the pipeline and the data frame. The data frame is in the Connell format, which is a common NER format. Once the project is initialized, you will be asked for an API token, so you simply log into the platform, get an API token, and the training and evaluation can begin. Once the training is finished, depending on the size of your dataset, this can take around 5 to 20 minutes. You can see the results in the console. On the right center side, you will see the rows, and you will see a score assigned to each row. A higher score means a higher difficulty for the model to label this label. On the left side, you see insights. For example, high frequency problematic words, likely mislabeled words, class overlaps. If you go into the metrics, you can see overlapping classes, most common error types. And let's go through some examples. The algorithm has detected that actually tumor is labeled as a tumor, and in the original dataset as an invasion. Another example, the metasis is labeled as a historical type or labeled as metasis. As you can see with the class overlaps, these are difficult cases where it might be difficult for the modeler to labeler to decide which group it is. Galileo makes it easy to find these difficulties and provide quality datasets for training stronger models. For example, in row 656, A is labeled as metasis. Clearly, this is a mislabel. And in the example above, you can see the whole sentence labeled as pathological result, and maybe you could argue it's only the first part of the sentence. Once you find your mislabeled data, you can correct it and export the corrected data frame. Lastly, we also show embeddings, which makes it easy to select groups and clusters. Based on these clusters, also maybe find mislabeled data or label specific clusters automatically.
All right. So I hope that was super interesting. I'll now like to walk us through some of the next steps in going into the algorithms that really power some of the insights that you just saw. So first, I do want to talk about what is data error potential. Like, one of the insights that you might have seen in the demo is detecting the bad data itself and detecting what was hard for the model. So the way this works is, when we fine tune your models with Galileo hooked in, we literally sample. So Galileo's Python client uh, uh, easily quickly samples the required information from your model. And the way we compute insights is by instrumenting all these insights as your model trains. So what is data error potential, right? So data error potential is the measure of um, how each row in your data set was useful for your model to converge on and perform better on that data set. So as your model fine tunes on top of the data, epoch over epoch, or even if it's a single epoch and you're just fine tuning the last step, uh, all you need uh, all you need to do is hook in Galileo, and we look at how your model's layers are converging on every row in the data set. Um, and we look basically the math behind it is, we look at area under margin, which is basically the top probability, like p of y star, and then we subtract it with the probability of the maximum prediction in your probability range, for your, of course, in your probability distribution, right? So this is done for every single prediction, every single token, or every single span, whether it's a classification, NER, or generative model. And I'll show you some examples there as well. Um, and so what this does is, essentially, the intuition is that if your model found it really hard to train on, that it could surface um, one of the following issues. Firstly, the model could find, be really, actually, the model could be really biased against that data set. So for, mainly for foundational models that are large and trained on large corpuses, uh, there are imbalances in the data set and skews which prevent your model from learning the or converging on the features from your particular subset of the data. Secondly, there could be errors in the data. It could be labeling or annotation errors. It could just be that the data is garbage, or not of the typical expected type. We often find depth to surface data that is like either in a different language, or it's just mistyped, and you're expecting the model to learn from that. um, Third, we dep uncovers data that is on the decision boundary, which is really confusing for the model. And oftentimes you need more such data to make your model train better. And lastly, it could just be that the type of data that you're trying to train with is super sparse. It's some of these outlier kind of data points that aren't in statistically sufficiently present in your data set to be able to train on. So next, the data error potential can also manifest itself in actually giving us a nice visual overlay of our entire data set. We can quickly identify pockets of erroneous data, and the data that we need to pay attention on as data scientists, to quickly improve our models. You can see how this is an NER run, as we saw in the demo, and we can also see how depth highlights the spans that were really hard to predict, and the model didn't really get them. So this is, as we see, as you lasso over this region, we can actually identify super useful patterns. Next is another useful algorithm that we call semantic drift. Galileo's actually worked for a long time on developing this algorithm. Semantic drift, in its essence, is um, the uh, the identification of truly semantically drifted data, or different data in production, or in an unlabeled corpus of data. This is super critical for us to keep augmenting our data sets to make them even better and more robust in production. Oftentimes we just add a bunch of data, like we just throw the whole kitchen sink at the problem, add a new bulk data set to our models, and we see that our model will actually regress in performance on certain in certain cases. And that's because we're adding more data of a specific type where the model was already doing well. It's only adding to the model's confusion in capturing that space now. Whereas if we were to add the data samples that were actually lacking in the training data set, but we see more often than not in production or in our larger data corpus, that's the data that we should prioritize in getting annotated, in adding to our training data sets, and improving our test set coverage for it. So the way semantic drift works is that we look at two data planes here. The gray points there are your training data. The colored points are actually the drifted data, but they're a subset of the entire unlabeled or production data that we surface. And then this is the subset that Galileo automatically surfaces to our users to start prioritizing. And then between the two embedding spaces, what we essentially do is we have like a quick um, similarity distance algorithm. It's a graph based algorithm in the embedding space that looks at the k core distances, like basically the semantic distance in a to the k nearest neighbors in that graph. And so we've made it super fast and effective and scalable on millions of data points. Next, I'm going to be talking about LLMs here. We already saw a lot about NLP and in different task types there. Now with LLMs, right, one thing we found out, and we all know this, that LLMs are much bigger black boxes in the sense that they're trained on a lot more data, and they're a lot more opaque towards getting the true understanding of where is my model, where's the source of the generation coming from. These models are so generalizable. They're so broad in their domain space, that when we actually try to apply them to our enterprise use cases or our specific application use cases, we often don't know why the model is generating something. That actually gets that issue actually gets multiplied by the fact that it's really hard to evaluate these models in the first place. There's no we have some metrics like Blue Rouge, of course, and Perplexity, Bird Score, etc. But these metrics are again quantifiable statistical metrics, and they're not qualitative metrics. And what we've seen is with LLMs, we need a qualitative score to really understand where is my model really making a mistake, and why is my model not generating the right kind of stuff. So this is the LLM stack that we've been seeing, and with Galileo's LLM Studio, we actually have built out three different modules, which is the prompt inspector, the LLM fine tune debugger, and the LLM monitor. And what we've seen is the biggest challenges come from not being able to evaluate and compare different models, get to the best prompt really quick for our application. And even just the biggest thing we've heard is that oftentimes you have to do a human eval to gauge which model and which prompt is better. Secondly, with vector databases, you're not oftentimes sure of like whether we have sufficient context, or is there too much context on that side, and how is the context being used or utilized by the model to service the prompt. And then lastly, there's the application layer, where we have a bunch of prompt orchestration going on. And in that orchestration layer, we need to oftentimes also check for guardrails, and make sure that there's no hallucinations going on. There's the model does not spit out any toxicity or PII or PHI, and then there aren't any cost or latency spikes because of changes in the prompt. So I think that's these all of these key pain points are in the favor of preventing, like, in the favor of kind of evaluating the models for better. So that's why Galileo is an evaluation first platform that helps us basically do three main things: prevent hallucination risks with LLMs, uh, improve our time to productionization and evaluate and experiment models faster, and provide a better governance and explainability layer so that we can add these checks in and balances in place to prevent hallucinations even when our applications are in production. Now, with this in mind, I'm going to again dive into some of the algorithms that Galileo surfaces to help us in this space of adapting LLMs to our own data. Here we of course we rely on a whole bunch of metrics, many of which have been developed at Galileo through, of course, building on top of cutting edge research in this space. So some of them are on the input side, where we help users improve their prompts and their context related to the prompt, and the others are on the output side, where we try to detect hallucinations, issues in the correctness of the model, uh, places where the model is completely uncertain and very likely to be random guessing, and then a whole bunch of other metrics, along with which our users also can define their own metrics, which are oftentimes application specific. If I'm building a chatbot for an oncology database, whether it's for patients or for clinics, these models are actually supposed to work well on oncology data. And now I better make sure as a developer that the model talks about terms, at least medical terms related to oncology, that are verified and vetted, and doesn't make up certain medical terms. And I've actually seen that happen when developing an application there. So one of the metrics that Galileo has developed is factuality, and this metric is oftentimes like just making sure that the model does not just make up facts. And the in this particular example, you can see how there's actually only average temperature and the maximum temperature mentioned in the prompt, but your when the question is asked, like, what's the median temperature in this range, the context does not have any information to compute median temperature actually, and the model generates a response that seems that seems really really accurate. Or and to a human eye, like I would think that, oh, okay, the model has given me some reasonable output without giving it a double a thought again. But that's where our the factuality metrics shines. And if you look at the last couple of lines in the explanation for why factuality is low in this case, it says that, however, like, the claim is not the claim is it's not factually correct, because there is no median temperature in the context, and there are no means to compute it. The Again, coming back to data error potential, but in case of sequence to sequence and models and LLMs, it becomes even more critical. In this case, this entire passage, this is a summarization model, and this entire passage is trained on was actually all about the Japanese automakers, the Japanese uh, uh, company Sony and its shares, and the ground truth is actually all about the shares the shares of a Japanese automaker, Mitsubishi. um, and it's super cool to see like how depth can surface errors in the ground truth, because there was in the in the first main paragraph, there's no mention of an automaker. It's all about uh, this electronics giant Sony. and the transcript all talks about an automaker, Mitsubishi. So now now that we've gone deeper into the algorithm space here, I want to hand it over to Christian to take us through some of the cool developments of Spark NLP and some of its capabilities there.
Cool. So thank you so much, Franz, for this wonderful demo, and also Yash for this wonderful introduction. Now that you have seen how you can sharpen your tools with the Galileo toolkit, let me teach you a little bit about the tool itself, Spark NLP and the Jones Snow Labs ecosystem. Spark NLP is a big data library focused on being the most accurate, fastest, and scalable out there. And in its 6 years since its inception, it has accumulated over 50 million downloads and has become the most widely used NLP library in the industry and set various benchmarks for the most accurate models in the industry and also in the whole research community for especially many of the medical models and medical problems and domains. And all of this we have backed up with various peer-reviewed papers, and all of this hard work made us trusted by various Fortune 500 and enterprise customers and awarded and recognized with various awards by the industry. And if you look at all the features, you can really see why that is so. On the open source side, we have over 220,000 models in over 250 languages, which you can now analyze and tweak with the Galileo toolkit. And some of the tasks include the simple text pre-processing like sentence detection and tokenizing, but also all of the more advanced large LLM and deep learning based features like question answering, translating, summarization, text classification, and even non-standard data types for like speech to text generation, image classification, table question answering, and much, much more. This is powered by the latest and greatest transformer-based architectures like BERT, Elmo, Tapas, T5, GPT, and many more. And on the enterprise healthcare side, we have over 1,000 models for various highly specific medical domains and problems like proteins, pathogens, phenotypes, various demographics, and many other types of domains and problems which you usually don't get out there that easily. We have large teams of medical experts labeling data sets and creating the best models for these problems out there. And not only that, you even get more advanced features like relation extraction, assertion status, and entity linking to solve even more complex problems and gain even more data and more value from your data. And of course, one of the core and popular features in the healthcare sector, things like de-identification. And all of this, we keep adding all of the transformers, so you can always be sure, right? You don't need to read the paper or do any of the hard work. We do that for you, and we keep adding the new, latest and greatest architectures, so you don't have to worry about which those are. And all of these features are available in most of the common languages like Python, Scala, or R, and in all of the common environments like AWS or Azure or GCP, and even with highly optimized builds for M1 or M2 Apple chips, GPUs from NVIDIA, or even AWS Graviton machines. And if you're curious for more and what you can do with the library, everything you learned about, you can optimize and tweak with the powerful Galileo toolkit. It essentially enhances your Spark NLP experience. And if you're curious for more, you can learn much more about this from all of the various features introduced by the Jones Snow Labs library. In just one line of code, you can explore text generation with large LLMs, or even table question answering with the Tapas architecture, image classification with VIT, speech to text with WAF2Rec, and even with the OCR library, you can extract the text from tables, or even extract text from images, PDFs, docs, docx files, and many, many more. For more, check out these resources. And now I give it back to Yash to give you a great outro. Thank you so much. Thanks.
Thanks a lot, Christian. So, so just to round this up, we've seen, some incredible insights about how we can improve our models and adapt our models towards our own data sets, and the amazing capabilities of Spark NLP. And in the end, I'd love to just close this out with an overview of where Galileo fits in. And so one of our key tenets has been to be an end-to-end platform that is evaluation first, and there are tons of metrics that we've built over the past several years, and so can't wait for you all to try it out. And I hope some of you all can also apply some of these methods in your day-to-day workflow. Please do visit our website. It's called rungalileo.io, and we have details about these algorithms and in our documentation. So do go and check it out. Thank you all.